So previously, you had worked on the Taylor polynomial for e to the x, and you obtained this result here. I just want to highlight a couple things that, in terms of the patterning, you could have put a factorial right here as well, because 2 factorial is 2. So you probably didn't put it there, but you could have. Even out here, you could have written 1 over 1 factorial, which is still 1x to the first. And even here, this 1, let me just put it down here. You could have expressed 1 as 1 over 0 factorial x to the 0. Yeah, 0 factorial is 1. X to the 0 is 1. So this thing right here is also 1. Now, here was the issue that I just want to emphasize, make sure you all are getting it. Here's the point. You make some Taylor polynomials for sine, for cosine, for e to the x, for natural log of x, like we did it in class. But once you have the basic family, and there's others too that we haven't done, but for tangent, for, I don't know, whatever function, just a basic function, from that family or that set of Taylor polynomials, you can get the Taylor polynomial for anything else. So, for instance, the one that we had done in the videos was sine of x over x. Okay, take the Taylor polynomial for sine of x, divide everything by x, you get a nice polynomial. Now you can do things like integrate that you couldn't have done before. Likewise here, suppose we wanted to integrate e to the negative x squared dx. You may recall from class that this integral actually is, there's no elementary function, there's no antiderivative for e to the negative x squared. But what if we were able to replace e to the negative x squared with a polynomial? Can you integrate a polynomial? Just say yes. So what if we could replace this with some polynomial? So here's the deal. Don't start from the whole derivative deal like you've seen. That is how you develop Taylor polynomials, but once you have a basic family of Taylor polynomials, then just build from there. Here's what I mean. If we know how e to the x works, we know how e to the negative x squared works. Because really what this is a composition. Notice that, let me just get a different color to try to make this more clear. Notice that what we've done is we've replaced the exponent of x with a negative x squared. So we can, in terms of the Taylor polynomial, do this. We can have our 1, we can have our plus x, but replace x with negative x squared. Instead of 1 over 2 factorial, or just 1 over 2, x squared, instead of just x squared, we're going to replace that x with negative x squared. And then likewise here, instead of x cubed, likewise here, instead of x to the 4th. And I'm going to run out of room here, but I hope you see that this would continue as a factorial. For all of those things, we're going to replace those x's with negative x squared. Negative x squared, negative x squared, negative x squared, negative x squared. All right, and so what that does for us is it produces a Taylor polynomial. Let me just write it in a little cleaner way. Plus a negative x squared, so it would be 1 minus x squared. Plus 1 over 2 factorial, negative x squared squared. If you took negative x squared, a negative times a negative is a positive, so you would get a positive x to the 4th. And then now here, if you took negative x squared and cubed it, a negative times a negative times a negative would be a negative, so it's going to be minus. And then x squared cubed, x squared times another x squared would be 4, times another x squared would be 6. Now a negative times itself 4 times would stay positive. That's a 1. And 2 times 4 is 8, so it would be x to the 8th. And then, let's see, a negative x squared to the 5th. Because it's the 5th, we're going to get a negative on that last term. That's going to be minus 1 over 5 factorial, and then x squared to the 5th is going to be x to the 10th. So I will guarantee you that if you were to graph e to the negative x squared, and barring something I've written down incorrectly here, this Taylor polynomial will resemble e to the negative x squared for a while. Of course, with all calculus, so much of calculus I should say, the whole idea of going off to infinity is really there too. So imagine this pattern, plus, minus, dot, 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 forever, never, never, then it would work. All right, so what's the point? Since we can't integrate e to the negative x squared, we could instead integrate the Taylor polynomial. That's the beauty of this. This is sort of the mathematical reasoning. One of the motivations for why we like Taylor polynomials is because they provide a tool for us. Now, in the case of your assignment, you were to integrate from 0 to 2. And just to kind of show you that this really works, I asked you first to integrate e to the negative x squared using technology. I'm going to jump to Desmos in a minute, but when you do this, it came out to be about 0.88 something. In fact, let's go look and see. Okay, I got it down here. There it is. That integral is 0.88208, etc. All right. So first of all, I just wanted you to see the Taylor polynomial. So here's y equals e to the x in red. I hope you recognize that famous exponential growth curve. Here is its Taylor polynomial. I took it out to, I think, to the 7th degree here, just to kind of get you to see that there is a nice match. Of course, a 7th degree polynomial eventually is going to diverge away from e to the x out here, but it's good for a while. If I put more terms, the convergence would be even better. In fact, take a look. If we do a bigger polynomial, more terms is what I mean by bigger. Look at that. With a 23rd degree polynomial, at least in this viewing window, we're pretty good. Oh, there it goes. Well, go a little more. All right, there it goes. So you can see the more terms that you have, the better the match. All right, and then there's the integral. Okay, so then we can integrate e to the negative x squared. Now, I want you to make sure you're clear on what's happening here with Desmos. Notice here, g of x is that polynomial that we were just working on here. Let me get a not as good one. Let me bounce it back to just a equals 5. We just now have from the 0th to the 5th term. So 0, 1, 2, 3, 4. You can't see the 5th one. But it's just those 5 terms. So if you were to integrate just those 5 terms with g of e to the negative x squared. Again, look at the substitution. I'm just replacing x with negative x squared. Notice the integral comes out to be only about 0.3 instead of 0.88. Well, add another term. Well, add another term. Well, add another term. Well, add another term. And I hope you see that now we're up to just 10 terms. With just 10 terms, we're doing pretty dang good there. Now you can even see it if you replace f of x. Remember, f of x was my e to the x Taylor polynomial. If you replace x with negative x squared and integrate, there's the 0.74 compared to what it should be, 0.88. Not bad, considering we don't have we only have 7 terms, I think it was in that case. What I had up here was out to the 7th degree. So this is not f to infinity and beyond. It's just the 7th degree. And we're already seeing pretty much some convergence. We're seeing that things are working the way they should. There it is. Yeah. The more terms you have, look at that, the more it converges. Now, back to paper and pencil. Like if you weren't working with Desmos, what you would do is take this Taylor polynomial here and just integrate it term by term. I'm not going to go through all the details here, but just if you wanted to work on it, you would say something like this. Well, the integral of e to the negative x squared would be first of all, the integral of 1. And the integral of 1 we know, of course, is x. And then the next term is minus x squared. And we know that the integral would be minus 1/3 x cubed. And then let me just do a couple more and then I'll stop here. The next one was 1/2 x to the 4th. And the integral of 1/2 x to the 4th. Let's see, it's going to be x to the 5th for sure. Got to kill the 5, so a 1/5, the 1/2 that was there, so it's going to be a 1/10 x to the 5th. Let's just do one more term. We had a 1/3 factorial x to the 6th. So let me just write it out here. We're going to have a 1/3 factorial. The x to the 6th is going to become an x to the 7th. We're going to have to kill the 7. So it's going to be like let's see, 3 factorial is 6. So it's going to be like a 1/42 x to the 7th. So just in terms of those first few terms, it's going to be x minus 1/3 x cubed plus 1/5 x to the, 1/10 x to the 5th minus 1/42 x to the 7th. And if we were going to evaluate this from 0 to 2 to get the definite integral as in your assignment, then you would just evaluate everything here at 2 minus at 0. Notice that at 0, everything is 0. So it's just going to be 2 minus 1/3 times 2 cubed plus 1/10 times 2 to the 5th minus 1/42 times 2 to the 7th. And I'll bet this is going to be in the ballpark of that 0.88 that we saw. Again, not that close because we're only doing a few terms, but I hope you would get the idea. But isn't it nice that we can kind of let Desmos do that work, that we can just generate that f of x, and then we can say, hey Desmos, go ahead and substitute negative x squared into that f of x, and we can see the integral result as well. Well, I hope that helps you. We're going to start with our basic family of Taylor polynomials, and then we're going to build on them. Like you could take sine of x and just divide everything by x. You could take e to the x and replace all the x's with negative x squared, a composition of functions. You can build the function you need based on the few that we have in our Taylor polynomial library. Take that to the bank and deposit it.